Okay, hi, good afternoon, everyone. So I think let's start. So just to introduce myself, thank you for joining today. My name is Guglielmo Iuzia. 1 month and a half ago I joined MSD in Ireland, and coming from Optum, which is another healthcare company, part of the United Health Group. And previously I was in IBM and FAO, which is an agency of the United Nations, headquarters in Rome, just to have a little bit of background of the last 11 years before joining MSD. And a few numbers about the company. So basically, in particular, focus on MSD in Ireland. The company is there since more than 50 years now, employing more than 2,000 people across 5 different sites and 4 different locations. A lot of investment. So at the moment, it ranks in the top 20 company having business in Ireland. And I'm sitting on the new MSD biotech facility I'm part of MMD, Merck Manufacturing Division. All of the effort, me and the team, other teams in Prague in US involved in these projects will be aimed to improve the manufacturing process for some of the products we have, in particular for the Keytruda in the immuno-oncology space. Today I'm going to share my experience across different projects, different companies, a personal project on doing deep learning, in particular training deep learning on a Spark cluster, which is a sort of a challenge if you are in deep learning, probably you already know. Before I start, a quick poll. How many people do deep learning in a production project? Okay, that's good. So because I didn't put any details on deep learning itself, so it's good. How many people use Spark in a production project? Oh, that's good. So I could skip the Spark slide as well. Good, because there are several use cases. We'll focus on the main topic. And one last poll: how many people come from a Java or Scala background? Okay, some people coming from Python. Okay, so the good news for the Java Scala developers is that there are use cases in this space. I didn't prepare anything with Python, but anyway, it's possible in this space to import existing model in TensorFlow or Keras, but that will require probably 8 hours just to present the topic. So you have to wait for another presentation for that. But anyway, there is enough on this. So deep learning basically is a subset of machine learning where you focus on using deep neural networks. And basically deep neural network, you know, it has an input layer, an output layer, and a given number of internal layers. Depending on the particular scope of your application, the implementation could be different. There are several models proposed in time by historically since some of them since the 70s, the 80s, up to recent implementation proposal by companies like Google or Microsoft. There are several cases of doing deep learning in the real world, in computer vision, text generation, natural language understanding. In the last 1 year and a half, I saw a lot of new projects coming in the quantitative finance, gaming, robotics, and many others, biotech as well. I hope more next. So it's not just for fun. There are real applications for this. It's not just a hype. Today I'm going to talk about the 3 open source technologies that we put together in order to train deep neural network in a distributed fashion on top of Spark. And what are the challenges on putting these things and working in the real data in your production environment? So the first framework I'm going to talk about is the Deep Learning 4J. It's an open source framework for distributed deep learning on top of the JVM. So it means that if you write your application or if you Spark your Spark jobs using Java, Scala, Kotlin, or whatever runs on the JVM, that's the framework for you. There is also porting for Android. I've never tested it, but anyway, there is a JVM on Android devices, so it's supported as well. And the interesting thing of this framework is that since the first release, it's integrated with Hadoop Apache Spark. So it shares the same execution model with Spark. So you don't have to reinvent the wheel, do a lot of unnecessary extra work to run these things on Spark, of course, if you use Spark. So it's a very high-level language. And the same things, the same code can run both on GPUs or CPUs or a mixed environment. You don't have to change your code. If you switch between GPUs and CPUs, you have just to change the configuration of your application, and that's it. This framework is modular, is not monolithic. There are several modules and more are going to be added. This is just a short list. If you want to see the full list, you go to the GitHub repos for this project. The most important probably are DataWorks, because basically it's the module that converts any input into vectors, because in order to train your models, you need to use vectors. And by input, basically DataWorks manage almost everything. The input could be not just text, could be images, videos, audios, any kind of structure or unstructured content, and different formats for them. There are several implementation of the record reader interface, just in case there is some particular input type or some format not supported. You can implement yourself that interface and handle those particular data. Arbiter is the module for hyperparameter optimization, and then is the core module to build, configure, and define your neural networks. Dataset is a new package. Basically, is some sort of high-level wrapper of the most common public available dataset in the net, such as the Cypher10 or the MINST. So if you don't want to download the package, there is this facility as well. RL4J is a module for reinforcement learning. So this is a framework is really not just for pure deep learning. DL4J Spark, of course, is the module to do things on top of Spark. And I'm going to talk about ND4J in a few seconds. I want just to show you a simple example of DL4J code. This is in Java, but as you can see, it's a very high level. So anytime you need to configure a neural network, whatever the model you're going to use is, you always use the same object, which is you have a multi-layer configuration object, and then you define all of the properties for it, such as, for example, the updater, the strategy you want to use for the weight initialization, and then add a list of all of the layers. In this case, this example is a convolutional neural networks. As you can see, the first layer is a fully convolutional layer. The second one is a max pooling, and so on. And this is the same process, whatever the network is, not just for CNN. And the code on the right, an example of how you can then train your network in your environment, and you use the specific fit method for the network object, and you can do evaluation across epochs. While you're training your network, you can perform evaluation on the fly and see some result on the fly as well. So the second piece of this architecture is ND4J. This has been born as a module of Deep Learning 4J, but now is some sort of independent project. So basically, it's an open source framework for linear algebra and matrix manipulation. It tries to bridge the gap between Python and the JVM programming languages in terms of availability of tools, libraries for linear algebra. The inspiration for these tools is NumPy. If you're in Python, probably you know better NumPy. It's more or less the same syntax. The difference is that from a developer perspective, you code in Scala or Java. Behind the scene, the implementation has been done in C++ or CUDA, depending if you're running on CPU or GPU. But this is transparent to you. So you write your application in some JVM languages and then set up your configuration, and it's up to ND4J to do the dirty job behind the scene with the low-level language closest to the hardware as much as possible. The third one, of course, is Spark. So I think I could skip this slide. Everyone, I think, is aware of what Spark is. And it's important to understand why these three technologies combined together are a powerful tool for training deep neural networks in a distributed fashion. So each one of these technologies brings something to the plate. Deep Learning 4J, as you saw before in that couple of examples, is a very high-level API. So Adam Gibson and the other guys that implemented had the idea of this framework were coming from a software engineering background. So they want to create some sort of tool for software engineering to upskill into deep learning or machine learning. So keeping this in mind, they try to have very high-level API so that reading the code, software engineers start to understand the principle behind multilayer neural networks and deep learning. But of course, deep learning 4J in some cases couldn't be enough, because depending on the data you have and the particular use case, you will need to do some training in distributed mode. And Spark has been born for this. You know about the performance of Spark. The problem is that for several cases of training, that particular computation cannot rely on doing just transformation, aggregation, calculation on top of the JVM in some JVM language. You need to do something else at a low level, using a low-level language, and this would improve both performance and accuracy of your models. Then ND4J comes to the rescue, because Deep Learning 4J uses ND4J behind the scene anyway. And so it means that some of these calculations are executed in C++ or CUDA at a low level, and combining these three things together, you achieve the best results in when training your models. And a word before moving into the main topic about a different way of doing distributed training. You can choose to do data parallelization or model parallelization. Data parallelization means that you train the exact same model on all of the nodes of your cluster, but with different set of data. Model parallelization means that each node is responsible for the training of a single layer of your model, and the training happens with having on each node the same data. Of course, data parallelization, it's easier to configure and manage, so most part of the examples you will see are related to data parallelization. Next releases of Deep Learning 4J will provide more facilities to do model parallelization on top of Spark. But anyway, this is if you do data parallelization rather than model parallelization, is not a critical issue at all. So that said, we saw the good news, but what could possibly go wrong doing these things in a real use case scenario? So let's start from memory management. Here, where things are a little bit different from traditional Java or Scala applications. Before I move on into these topics, just to tell you that all of the best practices that you know on doing Java, Scala development, or doing things on Spark, or if you're coming from a data science background, on picking up the right model for the particular problem, all of them apply in this case. So I'm assuming now that you are in good shape for this, and these are problems that are extra addition, combining these technologies together. So the first one is about memory management. If you observe this snapshot, this is related to some model training on multiple nodes. This is specific for a single node. And you can see on the chart on the top that there are two lines. There is the red line, which is almost constant. It represents the utilization of the heap memory by that particular job in this particular node. You can see also another blue line going up and down with significant variance in time. And that represents the utilization of off-heap memory. This is a situation where the training is doing good, so it's not an exception. So this is a little bit different of most part of traditional traditional Java Scala application, where probably there is not the same variation utilization of its memory. So this is something that you have to consider doing consideration about memory management, and not only memory management, as you can see in a few minutes. And this is the case of CPU. I deliberately took a snapshot on something running on CPU. If you observe the same with the GPU, you will see much more of its memory utilization, of course, as expected. So you need to take into account this when implementing your code on top of Spark. And there are two approaches you could do on doing memory management with deep learning for J, and in particular when you go on top of Spark. JVM GC and wake reference tracking, or memory workspaces. The first one is nothing new. If you're familiar with Java or Scala, it's the same stuff that you do every day. Memory workspace is a feature of deep learning for J. They come from the same idea. So once a multidimensional array is no longer required, so we need that the memory it was utilizing needs to be released so that some other object could reuse it. So that's the same principle. The difference is that for the JVM GC, anytime a multidimensional array is collected by the garbage collector, this of-heap memory is deallocated with the assumption that is not used anymore. While with memory workspaces, this memory is released. It could be reused without the allocation or reallocation. So this is a better case in most scenarios, not all of them, with deep learning for J on top of Spark, because there are a lot of objects going on into the off-heap space. These two solutions, basically, it's impossible to say one is better than other. It depends by the specific scenario. There is one thing that you have to keep in mind if you choose memory workspaces. It's a little configuration, but it's really important. Anytime you want to move to memory workspaces, please don't forget to disable, if possible, the garbage collector. There is a facility through ND4J to turn it off, or if not possible, because it could be that there are several objects in the JVM heap memory as well, you can reduce the frequency of the GC calls using another method provided by ND4J. This is important because if you forget to do this and you set up your application to use memory workspaces, it's the exact same situation you have with the JVM GC. So you're not doing memory workspaces. It's a simple thing that is hidden in the documentation, so people don't know, including my team, so a long time ago this. One of the facilities provided by Deep Learning for J is a real-time dashboard. This starts when your training starts. It's alive during the whole duration of your training, and it's a brilliant and useful tool because you have lots of charts. This is just the homepage where you can check almost anything on understanding how your training is doing. So a training could last hours, days. Sometimes you start it, then you come back after hours or days and realize that you screw up some things in the configuration or something, and choosing the intervals for during the hyperparameter tuning phase or some Spark configuration, whatever. Through this chart, you have a full picture at runtime. You have also details about each single layer of your network. And then you could decide to say, if you spot something that is not expected, to stop the training and then make your changes and start again the training. So this could be, can you hear my voice? Okay. So, so this is important. There is just one problem when running this on Spark, but it's easy to solve. So there is a dependency conflict between the DL4J UI module, which is the server that starts this dashboard, and Spark itself, the Spark core. So it means that if you try to run this on your cluster, you receive some errors, and basically the training happens as expected, but you don't see any dashboard. There are two options here. The first one is to the same module, DL4J UI, provide provides some facilities to save the training stats at runtime. So you could save this and then start the dashboard, the standalone, at the end of the training to do your analysis. But of course, this way, you're going to lose the advantage of something that could help you at runtime. The trick is to execute this UI in a separate process. So it's a separate JVM, not the same where you're running the driver and the workers in Spark. And then DL4J allows you to send the data to the JVM process that runs the dashboard and see the result at runtime, so which is more useful. This has been added to the documentation now. This is one of the things that people were banging their head on the Stack Overflow wall for a while. Okay, serialization. Yes, so you know, coming from Spark, you have two options in terms of data serialization. It's Java, which works with object output streams, is the default if you don't specify anything in Spark, or you could use the Cryo framework. Pro and cons of these two approaches are that Java basically supports whatever you implement if you just implement the serializable interface. So basically, you can do serialization with this approach on almost everything. But the size of the serialized object is big. So in order to improve performance and when you have or save space when caching these things, this object in memory or moving objects across the network is not the best option. Cryo produces smaller serialized object. The con is that it doesn't support all of the classes that implements the serializable interface. But anyway, this Cryo is the best choice often for the objects supported there. So people coming from Spark and starting with deep learning with Any4J, of course, choose Cryo. And this is a good choice, but be prepared to receive a lot of null pointer exceptions because the problem is that the Cryo framework itself doesn't work very well for off-heap data structure because the implementation, of course, didn't have any use cases of so large objects or so many objects into the off-heap memory space. But ND4J comes to the rescue. There is another module which is not very well advertised in the documentation of the project, which is called ND4J Cryo. Basically, is their implementation to handle this serialized object in the off-heap memory. And from your perspective, you have just to configure your Spark application to use this serializer provided by Any4J, and you wouldn't see anymore all those exceptions that starting pop up almost randomly in your cluster. So it's a very simple tip, but are things that unfortunately often are not covered by the documentation, and people discover that by experience only. Data locality, of course, you know, in Spark this affects performances, and this is the way Spark performs data locality. It tries to move first the code rather than the data, of course, because the code is supposed to be smaller than the data you're using for your application. When it's not possible, tries to move the data following certain rules. So Spark has different data locality levels. It tries to wait for a while to see if there is some CPU available to process those data. If not, tries to move the data to another CPU or another node where there is computational power available. This is something that works very well for Spark's application. The default time for Spark to wait to a CPU to be free is 3 seconds, unless you change it in your configuration. And this works fine, but moving to the Any4J, this is bad because the training is computationally expensive, as I mentioned initially when I explained the reason why you have to combine these 3 technologies together. So if you let Spark to wait for a given time, even if it's just 3 seconds, this is really bad. Your training will last forever. there is one thing that you have to do. So basically, you have to tell Spark in your configuration that please don't wait for a CPU, just move the data as much as possible, because the benchmark shows that computation time is more critical for training neural networks on top of Spark rather than network transfer and shuffling. So this is the perfect compromise to reduce time of your training and have a more smart utilization of resources, of CPU resources of your cluster. And this is simple to configure because probably you know already this. If you put Spark locality wait configuration property to 0, Spark knows that it doesn't have to wait anymore, and this is really going to boost your performances during the training. Oh, the off-heap again, so this is done off-heap. So, of course, basically, that's another problem. Spark basically doesn't know how to handle the space occupied by object into off-heap. Imagine you have an RDD, and this RDD of data sets of ND array. In this slide, I forgot to put some note. Dataset is not the dataset belonging to the Spark API, but it's the dataset belonging to ND4J. So basically what happens that when Spark has to drop RDD based on the estimated size into blocks, doesn't take into account the space that that object is occupying in the off-heap memory. So it means that in situation when you're doing memory only or memory and disk persistence strategy, the calculation is wrong, and this leads to several out-of-memory errors that are really hard to understand, because you see this in the Spark logs, or if you have some way to catch up these errors in your jobs, but you cannot understand what's the root cause. So this requires a lot of analysis before you can understand what's that the problem is that Spark can't handle this part of the object in the off-heap space. So this means that this is a quick trick. You just use, rather than use memory only, use the memory only ser level and memory in disk ser if you're using memory in disk level when persisting RDD or dataset or ND arrays. This means that in their serialized form, this object that doesn't have anything into the off-heap space. So everything is contained into the heap, and then Spark knows how to handle this, and then you are back to the situation where your Spark jobs work properly in terms of managing objects in memory and disposing these objects when they aren't needed anymore. Okay, this is the last examples. There are different things I would like to talk today, but I know the time is running out, I think. So this is an example. The examples shown before are related to different Spark deployments. So if you're running on a Yarn or still running on Mesos, or you're experimenting with Kubernetes or standalone, all of the stuff apply there. This is more specific on data preparation for images processing when you have your data in a distributed file system, such as HDFS, probably on your Cloudera distribution. Or the same applies if you have these objects, these images in a distributed object store, such as Amazon S3 or on-prem in Mini or whatever S3 based. This is specific to convolutional neural network. This kind of network are used mostly for image classification or those cases of object detections. And inside the network, you have each layer has a different implementation. And basically, if you look at this example, you see there is an image of a robot. Typical question you could address with a convolutional network is understand if the subject is a robot or a human, if it's sitting or standing, if there is a particular color in the figure, things like this. And of course, you train the network with images. Your input are images. If you're running this on a single machine, imagine you have a single powerful machine with lots of GPUs, probably you will need to use Spark. And the problem doesn't exist because there is a class in DataWorks called the image record reader that does the preprocessing for you, and that's it. But in case of Spark cluster, there are some tips that you can do before starting the training in order to improve the performance of the training itself then. Imagine you are some case where you're going to classify some vehicles. Imagine you have cars, trucks, motorbikes, bikes, and so on. You have to set up your images, the training set, into your file system. You have a root level of directory, which could have any name you like. The first level of subdirectory should have the labels of the images. So it means that this is the only thing that in the current implementation is not yet implemented in automated in Deep Learning 4J. Then the naming convention for the images is up to you. Because this is the way that Deep Learning 4J can pick up the labels for your classification. There's no other way. Then the trick is to preprocess the images into batches of file. Let me explain what is a file batch object that is provided by ND4J. When you receive the dataset, typically the images are not bitmaps. They have been compressed using some smarter algorithms such as JPEG, PNG, or other, and in order to save space and also improve network transfer for them. This is good. The problem is that if you have all of these single small images, you have a lot of read transfer in the network, and this will affect your performance during training. So the idea is to have collapse these images in batches. So this means you have for a batch a single read or a transfer, and this has the minimal impact on your performances. And there are two ways to do this. The first one is, imagine you receive these images locally. They are not stored in HDFS or something else. And so you have set up your local directory using the naming convention I showed you before. And then specify the destination directory in that server. Specify the size for the file batch object. In this case, I'm telling you, please put 32 images for a single batch. Of course, in production, you will have more. And then use a single method called create file batches local coming from the DL4J Spark module. And that's it. As soon as this is completed, you can send the data in your distributed system and start the training. Another approach could be, imagine there is some ingestion mechanism for these images in your HDFS, in your Cloudera environment, and then you set up a destination directory, of course also in HDFS, or if you do this in S3, please follow the naming convention about the class name, the class labels, and then there is a separate method for this, which is create file batch Spark, which works with a distributed file system or a distributed object storage. And then you don't need to move the images because are already there, ready to be used as input for your training. Then the second step is to create a data loader. I'm not going through this code, just look at the last line, which is the loader definition, where basically you take all of the properties and objects you defined before. You specify the number of classes. That automatically picks up the names from the first level of subdirectories, and then set up the preprocessor into the loader object. And finally, you can start training, and the code is the same. So once you're done this, is the exact same situation for your network for any or the other situation you could have, neural network or any CNN implementation. This is the last example. I collect some of these things and other into a book. So it's hitting the charts in the torrent downloads, so that's a good sign. So if you're interested in hear more, I will try to put in the next months more content on my blog as well, but feel free to ping me anyway on LinkedIn or through Twitter or my blog, so I'm available. I'm around anyway for the next couple of 2 or 3 hours, so if you have any questions or whatever, I'm here. So that was the last one, so let's use the remaining minutes for questions. Yes, please.
What about the Python APIs?
Okay, good question. Yeah, it's not covered here. So basically, I forgot to mention in the list of DL4J modules that there is a module called import, which basically allows importing of existing models implemented in Keras with a TensorFlow or any other backend, or directly in TensorFlow. How it works? So basically, you have two choices. If you already train your models in elsewhere, you can just import the weights and also the network configuration if you need it. And the execution happens in a sort of Java or Scala wrapper on top of DL4J or DL4J and Spark. So it means that everything runs on the JVM, but implementation of the model is done elsewhere, but someone expert in Python. It's possible to retrain the model here. Imagine you're receiving this model by some other team that did the training, but you have a different data set and you want to improve the accuracy with your data or do something which is more tailored for your needs. And then you can do the same, basically import the model definition as well, and then restart the training the exact same way, so with the same configuration about memory management and all the rest, serialization, and of course you could use the dashboard and all of the facility there. Yes, please.
How does the libraries function advice compare to some other implementations, for example H2O, in terms of performance and in terms of completeness?
Oh, basically when we start this journey 1 year and a half ago, we evaluated this library with another one called Big DL. There was no much choice in terms of open source because the constraint was to use just pure open source libraries for this training. And what we found here, but for the easy of use, because I used to manage cross-functional teams where you have data scientists and software engineers with different skills, and we have to find someone where everyone was on the same page. In terms of performances, this is really good. We did also comparison with Big DL, and this was much far away better. And the only use case where we didn't find good performance was comparing importing TensorFlow models into this framework and doing the training on top of Spark, and doing the same training on GPUs with TensorFlow only in a distributed mode is way more performant. So if your organization has a good availability of GPUs, use TensorFlow, don't use this. But compared with Big DL in terms of performance, was far away better. We didn't do any comparison with H2IO. We later, that were the only two options fully open source we had. A third option came up after 6-7 months. We started to do the first project called Deep Learning .Scala. It's by ThoughtWorks, but it was still not major for production. Didn't provide any way to import existing model in Python, and which we had some of those models. And it was much more data scientist oriented. So there was a shift into the perspective of this framework. So this way you have also Scala developers upskilling into data science, and while with deep learning for Scala was really, really hard because you have to already have a good skills in machine learning and deep learning before you could use the APIs. Another question? Yeah.
In one of the slides, you mentioned that one task per execute.
Yeah, this is.
Because the recommended is like we are running 2 to 3 tasks because underutilizing code will be there.
Yeah, no, in this case it's good. It's a choice by the implementation of the framework. Because if you remember that slide, I was suggesting to put the wait time for Spark to 0. And this helps because you're sure that you already know that there is a single task. So Spark and the N4J this way know they have to move, and they're sure that if they found some free CPU, they could check if there is a running task or not. And this is something that you could check if you use some tools like Spark Lens. If you do a dry run with a Spark job implemented this way, you can check the behavior, understand the model, and see how it works and why this choice has been done. Any other question? Okay, so if there are no other question, anyway, I'm around for next 2 or 3 hours. Thank you again, guys.